And we go to the next celebrity talk by Henry Neur for postdoc poster winner, and he will talk about the searches for directly imaged low mass companion to young M dwarfs. And please introduce your postdoc situation. Where did you graduate from with your PhD?
Okay. Hello. Okay, great. So my name is Henry Neur, and I graduated last year from Caltech Planetary Sciences with my PhD, and now I'm currently a Plaskett postdoctoral fellow. Just finished my first year at NRC Hertzsprung, which is located at the DAO in Victoria, BC, in Canada. And I would like to say thank you everyone for coming to see my poster this week. I had a lot of fun talking about my poster with you, and thank you to the SOC and the LOC for giving me this opportunity to present my poster. This is work done near the end of my PhD, the data collected and the analysis performed in the past year with Dimitri Mawey at Caltech and many other collaborators at Caltech and UCLA and beyond. So today, I will be talking about big planets and little stars. So you might guess I come from an exoplanet background as well, so I apologize for that. But this is the plot that you see pretty often in Exoplanet Conference, but I don't think we've seen it yet this week. So this is showing a mass of planets on the y-axis versus semi-major axis on the x-axis, and each point is color-coded to the detection mechanism for each planet. And I think this is the laser pointer. Yes, okay, great. So the goal of the survey that I'm leading is actually to image giant planets within 10 AU of the host stars. And if you look at this plot, looking at these purple points, these are all the directly imaged objects. You don't see very many of them within 1 to 10 AU. However, you do see a lot of green points. So microlensing surveys have predicted a large population of giant planets between 1 to 10 AU. But the other reason why we want to know more about these objects is to answer questions about the more distant cool objects. Are these the biggest planets that we know about, or the coolest stars that are in existence? And the way to answer this question is to compare it to something we do know of planets, such as the radial velocity planets that Jacob had just talked about. So if we take a look at the way phase space works here, the image planets basically span from thousands of AU away all the way into 10 AU. And the RV planets go out to about 10 AU. So there's this missing link. We would really like to have fill in this gap and see more directly imaged planets in here so that we can directly compare them with the RV planets. And I know I've seen many other posters this week that actually ask the same questions as well. So that would be really nice, but imaging planets is really hard. I would say that imaging planets is really the 5th difficulty level. However, hard things are not impossible. We can do it. We have the right instrumentation, and we have the right target selection. So let's talk about instrumentation first. So we want to use something to block out the bright starlight in order to see the faint planets. However, when starlight goes through the atmosphere, it's smeared out by the air that keeps us alive, and it makes the stars look very pretty, but they're not very useful for science. We have to use something like an adaptive optics system that then allows us to condense the cores and have nice, simple core PSF that are great for doing science because it's a lot easier to block them out. So then the next step is to use a coronagraph to block out these cores. So finding planets with a coronagraph is quite easy in principle. For example, you just basically block out the bright light and then a planet pops up. And it's all amazing. For us, we're using the Keck NERC2 L band, so 3.8 microns, vector vortex coronagraph. And here's an image of a scanning electron microscope image of it. It's etched out of diamond, that's what I meant to say. And here's also an image of it in the lab. So this is not the actual coronagraph on Keck, this is in Dimitri Mawey's lab. And we can talk more about this coronagraph offline. So that's the instrumentation, a good AO system to condense the cores and a coronagraph to block out the bright light. Now we have to think about how do we choose targets to maximize our chances of finding planets. So in our survey, we targeted up to 200 stars to look for planets. And we chose stars that are smaller and cooler so to improve the star-planet contrast. We chose younger stars so that the planets are still hot and bright because we're looking for emitted light. And we're choosing closer-in stars so that the small inner working angles that we can achieve corresponds to closer-in projected orbital separations, the 1 to 10 AU that we're looking for. So ultimately, all this adds up to young moving group stars as the ideal target. And in this review plot from Brennan Bowler's paper, we find that in the past decade, there's been a lot more young moving group discovered, and we heard this week that with Gaia, there's even more young moving group discovered, more memberships, more groups, and also more larger memberships. So there's going to be a lot more targets for stars for direct imaging surveys in the coming years, thanks to Gaia DR2. So for the technique that we use to image these planets, we use a common technique called angular differential imaging, ADI. And the way it works is explained by this small cartoon, where we have a star that, when it appears on the detector, doesn't appear quite like a point source. There's actually other speckles, other points of light near the central core due to the telescope optics and other uncorrected things from the atmosphere. So when you have these extra points of light, if you have a planet nearby, it can be pretty hard to tell them apart. Here I put them in two different colors, so it's a little easier, but in reality it's not so simple. So we have to use something to allow us to differentiate between the light coming from the telescope and non-physical sources compared to light coming from astrophysical sources like planets or brown dwarf companions. So what we do is we use the fact that the Earth rotates. So we turn off the field rotator on the telescope and take a series of images over a period of time. And over this period of time, things that are astrophysical in source coming from the sky will rotate and appear in a different place in our detector. Then we can take a look at the stationary components, subtract that out, and we're left with the planet. So that's the simple cartoon version, but it comes with a problem. When you're looking for close-in planets and you have low rotation on sky, so you don't spend too much time on each target, you have a problem for trying to find these really interesting close-in objects. Even after some significant amount of rotation, there's likely some position overlap between the first or the next or last position of the planet, so that when you subtract out the median or the stationary components, you basically subtract out a little bit of your planet light as well. So now you're less sensitive to planets due to this self-subtraction issue. So how do we get around self-subtraction? We use a different method called reference star differential imaging, also known as RDI. So in the simplest form, for every science star you look at, you spend half your time looking at your science star, and the other half looking at another star that's similar in spectral type, similar in size and other properties. And then you basically look for the similarities between the two stars, and everything is the same. You're basically measuring the same PSF. So you can subtract out the star light, and the leftover is the planet light. However, with our survey of almost 200 stars, this can be quite time-consuming to look at 200 other reference stars. So we're trying something new. We're using a library of science targets to create a reference PSF. That is, for our 200 stars, we use the other 100 and something stars, which are also measurements of the stellar PSF, and we can build a model reference PSF for every single science star and subtract that out instead. That way we don't spend any time doing dedicated reference stars. We're only looking at science targets. This comes with some challenges. We will need some kind of automatic pipeline to handle all of our data, as well as the database to kind of keep track of what star is going to be the most correlated and best to use for a reference PSF. So we were able to achieve this with the help of Wenhao Jerry Yuan. He's a rising senior at Pomona College, and he spent the last couple of summers and also the last entire year working with us at Caltech to basically build this automatic pipeline and create this database. And he's a very excellent student. He's applying for graduate schools this fall, so take a look, keep an eye out for his applications on your desk. So what have we been able to achieve? So this is called a contrast curve. It's basically a measurement of sensitivity to planets as a function of separation from the host star. The lower you are on this curve, the more sensitive you are to planets. The green curve tells you the sensitivity using that ADI, letting the sky rotate method, compared to RDI with our method of using other science stars as reference stars. So when we look close in, especially for separations of less than 0.3 arcseconds, we're actually 10 times more sensitive now to planets using RDI compared to ADI. And this is basically meets our science goals, because about 0.3 AU for the typical 0.3 arcseconds, I mean, for the typical distance of our star, this corresponds to those distances are less than 10 arcseconds. So Jerry actually didn't only do this pipeline database for us. He actually did a lot of interesting science as well. So he actually looked at all the data that came through the Node 2 vortex, about 360 stars, and he characterized how well Nook2 Vortex performs as a function of different stellar parameters in observing conditions and instrument conditions. And one of the interesting products that he has made is this question: when do we use ADI versus RDI? And the way you want to read this plot is, first you want to pick a separation where you want to find a planet, let's say 0.3 AU, sorry, 0.3 arcseconds. Then you go to the line and you read off the Y value, say 7 degrees. So this means that if you have enough time to stay on your target, so you get at least 7 degrees of rotation, you'll be above this curve, where ADI actually will do better. But if you don't have that time for at least 7 degrees, you're below this curve, where you're better off with RDI. So this really shows that the closer in you are, the more RDI wins. And in our survey, we actually have about 11 degrees of rotation. So RDI wins for any distances within 0.25 arcseconds. So this survey is actually now complete. We only got up to about 160 or so science targets, and we have 40 candidates to follow up. So I spent the last week looking through all the images again and making sure we didn't miss anything, because last Sunday, the first night of CoolStars, was actually our very first dedicated follow-up night. And we already started our follow-up campaign. We have some pretty interesting targets, such as this one. So this is something that is a cool star. It's very likely a brown dwarf. It's a delta L band magnitude of 5 magnitudes. And the other really interesting thing about it, besides being a cool star, is that it's 0.16 arcseconds separated. This is only 2 lambda over d at Keck on L band, and it corresponds exactly to our goal of trying to find planets or objects within 10 AU. After we find these objects, we generally follow up to ensure that they're actually co-moving. We also want to plot orbits. So I want to take a tiny bit of time to quickly plug Orbitize, which is our open source Python object-oriented extensible orbit fitting package for imaging astrometry. So it's originally built with Sarah Blunt's OFTI rejection sampling algorithm, as well as an MCMC orbit fitting for directly imaged objects. But we're planning to extend it to also take Gaia astrometry as well in order to fit orbits. This is on GitHub. We're looking for more contributors. We're going to release version 1.0 at the end of this month. You can follow the progress on GitHub. There's a milestone. There's a whole bunch of issues that we're still working on. Come take a look and see if you want to contribute. I just wanted to quickly mention Sarah's OFTI codes. It's ideal for directly imaging surveys because it's meant for cases where you only have a few data points over a short period of time, a couple of years, compared to the long 100 years orbit of the hundreds of years orbit. Orbital periods of directly imaged objects. And this does it much faster than MCMC, so take a look at Sarah's paper if you're interested for more detail. And then finally, if you don't want to wait till 2020 for the next CoolStars, I'd like to welcome you to Victoria in May 2019 if you're interested in the very, very low mass objects. We have a New Horizons and Planetary Systems conference. We're covering things from tests to planet formation, to disk chemistry, as well as planetary atmospheric chemistry, and also New Horizons KBO flyby this New Year's Day. So, in summary, we're trying to find the missing link of planets between 1 to 10 AU. We're using the L-band 3.8 micron vortex coronagraph on Keck, with original survey of 200 young nearby M stars. We had a lot of help from the automatic pipeline of Wenhao Jerry Zuan, who's applying for graduate schools. We have reference stars. We found that reference stars provide 10 times better sensitivity to planets. And we have a couple of follow-ups that we're doing, so please stay tuned for more. Thank you.
All right. Thank you very much for the nice talk. Questions here.
Mark Chiampapa, NSO. I was just wondering what your seeing criteria are. For example, when you constructed the reference image, what was the seeing limitations and in your application?
Right. So currently, we found that actually the best. So deciding how to best construct a reference image is still a work in progress. We have had a zeroth order approach is just to simply use all the other stars that were taken in the same night. So it seems like that actually does pretty well, which suggests to us that we want to consider similar seeing conditions. So we do track the seeing conditions from the telescope, and when we try to, moving forward, our plan is to use that database to figure out other stars that have similar seeing conditions and use them to build a reference model.
Okay. Yes, please, questions here?
Adam Burgess, UC San Diego. Was anyone able to explain your image?
Yes,
Your
actually.
poster image.
I actually gave away 2 drink tickets from it, and I'm gonna actually, I have some slides to show it. Sorry, let me just skip through it quickly. Yes, okay. So this is the image that's on my badge. It was also on Twitter. There's this weird happy face. So what happened in this image was that, spoiler alert, one of the other reference stars was actually not centered behind the coronagraph exactly, so a lot of light leaked out around the coronagraph. This created an extra bright ring in a reference image, so when you subtract it from the science image, you get a bright negative, a very negative ring, like a big hole. And then because there's also bright spots and speckles that are spurious, they just for this case, they just happen to line up in a way that you get a smiley face.
That's the way to make a smiley face. That's a great also way to finish this session and finish Cool Stars 20. And let's thank all speakers of this session and of this great workshop.